Welcome and thank you for joining us today. I will start by introducing myself. My name is Mui and I am the Customer Product Manager for the IFF Brewing and Distilling Enzymes. We are thrilled to be able to offer this technical webinar with IFF. This is a great opportunity for insight on some of the unique challenges of working with rye. I encourage you to ask questions or provide any comments that you may have during the presentation by using the Q&A button at the bottom of the Zoom window. We will address these at the end of the presentation. I'd like to start by introducing our presenter today, Andrew Fradiani. Andrew is the Senior Product Application Specialist for Brewing and Distilling Enzymes at IFF. Andrew has been a fan of the brewing and distilling industry since high school, where he realized that he could make more friends with beer. His previous positions include brewmaster for Pabst Brewing, as well as Yuengling & Son. He was the Senior Technical Sales Representative for BASF Refining Applications in Beverage, and was also a technical sales representative with Gusmer for the beverage industry. He's a member of the MBAA, the ASBC, and the Institute of Brewing and Distilling. Andrew has worked with numerous distilleries on process optimizations and has provided a great deal of support to the distilling industry. With that said, I'll hand it over to you, Andrew.
So thank you, everybody. And we'll get started here. On looking at rye, rye offers some very unique challenges when you're working with it in distilling. It's become very popular, and I think one of the things we have to deal with, the product that is in high demand is also one of the most difficult to make. So we'll walk through some things there, what's causing it, and how you can take care of it. So who is IFF? I think you might not know rye whiskey, recent sales. Some of the unique challenges when you're working with rye, what's causing it, where exactly does this come from, and how does it happen? And then we'll compare rye to some commonly used grains in distilling, other causes of viscosity, and in particular high viscosity, how to solve the problem, and some trial results with various enzyme applications. So if we're looking at rye particularly, this is always an impressive slide, that the growth of rye, if we're looking at the time period from 2009 to 2019, growth of 1,275%. And of course, if you're making rye, you're more aware of these numbers than I am. Tremendous growth. And the question is, why is there such a huge growth and demand for rye? And there's probably a few forces at play here. In general, today, consumers are demanding more and more an authentic experience. And we've discovered that in cocktails before Prohibition, rye was much more widely used than it is today, and even in our classic cocktails. So if you're thinking about a Manhattan or a whiskey sour or things like that. Another part is that in addition to that, the growing consumer demand for authenticity, Generation Z especially wants the authentic experience. And so they're going to be just 21 to 24, so mid, maybe late 20s today, looking for that authentic experience. And so they're looking more and more to rye. And so that the other part in there too would be, I would have to say, the popularity of the television series Mad Men, which you viewed on AMC, and Don Draper, and the cocktail culture of the 1960s. I also have to add we talk about the 3 martini lunch. Martini glasses were much smaller back then. They were about 3 ounces. So when you went to do a 3 martini lunch, you had a total of 9 ounces of cocktail in a lunch. I think that would still make me very sleepy today if I went out to attempt that. If you go out to a bar today, your martini glass is probably about 11 or 12 ounces. So 3 of those would be dangerous, I would say. You don't want to do that. So unique challenges for rye. First of all, it's low in starch when we compare it to corn. So there's a limit to the amount of starch that you can turn into fermentable sugar. There's a limit to the potential for ethanol when you are working with rye. Secondly, it has a very high water binding capacity, and we'll get into it. And that's really what makes rye such a challenge. It's because of this water binding capacity. So that means you can have a very difficult time in your mash with your agitator. You can get a stuck mash. Pumping your mash can also be very problematic. You're looking at plugged heat exchangers. It's a very sticky product, so cleaning needs to be more intensive. You can also get, if you have an open fermenter, you get these very large foam caps on the top of fermentation, and sometimes that can spill and overflow. So you have product loss there. What you might want to do then is reduce the fill height or the fill volume in your fermenter, but in effect, what you're doing is reducing your production capacity. You have also uneven flow in your column. If you have a distillation column, your balances can be upset and thrown out of whack. You also can get more fouling on the plates in your column. And what happens then is that you're shutting down more frequently to do a rinse, and eventually you'll shut down to CIP. So you're going to CIP more frequently. And finally, if you have a grains dryer, what's going to happen is that, again, due to this viscosity, you're going to see a slower flow rate through the dryer. You have longer contact time on your heating surfaces, and that can lead to a fire. So you can get dryer fires. This viscosity also leads to balls forming in your dried spent grains. So a lot of problems across the board from using rye, even though the demand for that remains high. So what's causing that? Specifically, it's the ARABINOXYLAN that is in the cell wall matrix of the rye that causes this trouble. So ARABINOXYLAN is a non-starch polysaccharide that, along with beta-glucans, offer some structural support and integrity to the grain. And so if you look over here on the right, ARABINOXYLAN are made up of a backbone of xylose sugars with arabinose spaced intermittently. And along that arabinose, again, intermittently, you'll find ferulic acid. So the backbone really is the xylose here with the arabinose here. To break it down, and this is what we want to do to reduce the viscosity, you want to break up this xylose backbone. So you need an enzyme that's going to fit here in this linkage here, the beta-1,4 link. And that specific enzyme is a xylanase. And so the more you can chop this up, ideally into one single xylose, the less the water binding capacity of the ARABINOXYLAN. And when you reduce the water binding capacity, then you can also reduce the viscosity. That's probably the biggest benefit of using a xylanase. The other one we'll see here later is that you can also increase your ethanol yield. So you'll see ARABINOXYLAN sometimes written as AX. You might also hear it called hemicellulose or pentosan. And pentosan is because both arabinose and xylose are 5-carbon sugars. Hemicellulose because it has characteristics similar to cellulose, almost. So this cell wall matrix needs to provide some structural integrity and strength to the seed so that it can survive out in nature, out in the field, survive over the winter, and germinate again in the spring when there's enough moisture and the temperature is warm enough. As that seed begins to germinate, it will produce its own enzymes that will break down this cell wall matrix and many other components, freeing up the nutrients, the stored nutrients that this seed requires to start growing. And if you look at cellulose, that's wood. Wood is very resilient. Wood can last much, much longer. And our houses are made out of wood. So thank God the houses last much longer. And some trees made out of cellulose can grow and live for thousands of years. So cellulose is extremely resilient. Hemicellulose, not as much. And it doesn't need to be as resilient. That's not the function of it. But we do need to break down these components in order to get to the nutrients in there. And that's also one of the reasons why ARABINOXYLAN can be so problematic. If you're using an unmalted grain such as rye, it never germinated. And so that seed never produced or synthesized any of the enzymes it needs to break these down. And so you're dealing with that in your mash. As I mentioned, the endosperm cell wall is located here in this portion, the center of the kernel, and also in the alurone layer surrounding that. And it surrounds the starch. So the starch is the primary carbohydrate nutrient. That's the sugar source for the growing seedling, but it's also the sugar source for us if we're going to distill and turn that starch into fermentable sugar that the yeast can then consume and turn into ethanol. In a typical distiller's mash, then you're depending upon the malt enzymes to do all of this work. So if you have a 95% rye mash, or if you have a bourbon mash with a high percentage of rye or even corn in it, you're usually looking at distiller's malt as 5% of your total grist bill. And so depending upon the timing and the malt that you have, 5% is not a lot. And you're depending upon the enzymes that are in the malt to break down all of this cell wall material to get rid of the ARABINOXYLAN and other components, and also to break down the starch. So there's a few things to keep in mind. 5% is not a very large amount. When we malt barley, so the germination and kilning process, and specifically kilning and the heat of kilning reduces the amount of enzymes that survive in that malt and get to your distillery. So the enzymes are temperature sensitive, and oftentimes the heat of kilning will inactivate those enzymes. So you have a very limited amount of enzymes that you're asking to do a lot of work. And so this is where it makes sense, especially in rye, to add some exogenous or commercial enzymes to help break down that endosperm cell wall, to break down those ARABINOXYLANs. And this here is looking at what we really want to go after. These are the starch granules. This is probably from corn. You'll see behind here, that's the endosperm cell wall. So the starch is really the main purpose of mashing. We want to turn that into fermentable sugar. The ARABINOXYLAN, those cell wall materials, are getting in the way. If we look a little bit closer here, this is a schematic of what the cell wall looks like. And it's if you look closely and think about it, it's almost like plywood, right? We have some very thin layers of ARABINOXYLAN. Between that is sandwiched some beta-glucan, and you have two of these cell walls. And between them, almost like plywood, where we put a resin between the very thin wooden plies, you have a protein middle lamella here. So all of this surrounds those starch granules that we just looked at. And all of this needs to be broken down so that water can get to the starch granules and enzymes can get to those starch granules. And so when we're grinding in a hammer mill, finally, because we want to be able to expose all those starch granules, we're also grinding these cell walls too. We make them into very small pieces, and that means they have a very large surface area and they can absorb a lot of water. And so when you start your mash, that whole combination leads to some very high levels of viscosity. And specifically then, if you're looking at the ARABINOXYLAN, again, the xylose here are the blue circles. You've got your arabinose here, the squares, so they're much less arabinose than xylose, and intermittently you have ferulic acid. When these ferulic acid molecules join to one another, so they're basically joining two ARABINOXYLAN chains, this is where you get the very high water binding capacity. But if you add an enzyme that can break the bond here between each xylose, you're chopping up this chain into smaller and smaller pieces. And by chopping it up into smaller and smaller pieces, you limit the amount of water that any one piece can hold. Therefore, you limit the increase in viscosity. So by chopping this up here, chopping up all that xylose, then you can reduce viscosity in the cook. So pretty simple, easier said than done. Next here, just looking at a comparison to the different grains that are commonly used. And I'll start with corn. Corn is widely used here in North America for many reasons. Number one, there's a lot of starch in corn, so we can get a lot of fermentable sugar out of there. It's grown abundantly here in the U.S., and so it's plentiful, easy to find. It has a lot of starch. From our perspective, as far as ARABINOXYLAN and the other non-starch polysaccharide beta-glucan, it's quite low, 0.03% and 0.05%. So very low and not too problematic. Your starch can be problematic for causing viscosity, but not these non-starch polysaccharides down here. If you look at rye, the percentage is far higher in rye. And so that's really the problem here. The ARABINOXYLAN in rye is what's causing the problem for us. Beta-glucan, a lot less, much lower level. Next, we have wheat. Keep an eye on that, or keep that in mind. Wheat also has ARABINOXYLANs, so much higher than corn, and that can be problematic. Beta-glucan also. If you can, and the starch back here on rye is quite low. I think I have right now the local municipality coming to clean the street, so you'll hear a vacuum in the background there. Rye, again, the amount of starch in rye is much lower compared to corn. So the potential there is going to be less. And that means you really want to break down those cell walls to get better access to the limited amount of starch that's available. Wheat is a little bit better. And then barley this year is probably raw barley rather than malted barley. That beta-glucan is fairly high, and barley is known, both barley and malted barley, for beta-glucan. Although recently now, in the past 2 or 3 years, it's been acknowledged that for barley breeders and maltsters, we've done a very good job over the past few decades of reducing beta-glucan in barley. But we're still having separation difficulties in the brew house. There's still viscosity problems. And we're starting now to focus on ARABINOXYLAN. And really nobody's measuring for that right now. If you use rye, you know that ARABINOXYLAN is a problem. So moving on here, and just 2 other things to keep in mind if you're experiencing high viscosity problems, if you want to do some troubleshooting. Starch, when it's not properly gelatinized, is going to cause issues with high viscosity. And I think we all know this from cooking. If you want to make a gravy or a sauce, you add flour to the pan, and that's going to help thicken up the gravy. Same thing is happening in your cook, although it's on a much larger scale. Beta-glucan, as I mentioned, also the other non-starch polysaccharide that you'll find in these grains, can also cause high viscosity. And for each one of those, you need a different enzyme to break down those materials and to reduce the viscosity. So for starch, you'll need an alpha amylase, and for beta-glucan, you need a beta-glucanase. So moving on here, we have high viscosity, and you might have experienced this and you're trying to figure out what to do. So there's a few options here. You can reduce the feed rate if you have a jet cooker or a continuous system. I think for most distillers, you're looking at lower fermenter fills. Or you can look at reduced solids. So can I reduce the amount of rye in the cook? If you have a certain recipe, you probably don't want to make any changes. If it's a 95% rye, you probably can't make any changes in that either. So, or making it thinner. So adding more water, it means you're going to get less ethanol out. Don't gelatinize. That's, I think, cold fermentation. You need to gelatinize your starch. That's going to be the best, most efficient way to and the first step in changing starch into fermentable sugar. Milling coarser is certainly an option. The coarser you grind, the less problems you have with viscosity, but when you're doing that, you're going to get less yield as well. And the converse of that is a finer grind will give you more yield. You're exposing more of the grain, you're making it smaller and smaller and exposing it to enzymes, so greater surface area. Reduced rye inclusion, that's what I just mentioned. The solids is just making a thinner mash. So you're going from maybe 22 beer gallons to 30 beer gallons. And so more water and less grain in there. And so all of these really don't offer a very good or practical solution. And so that's why really enzymes are going to be the most practical solution here, adding exogenous or commercial enzymes. So now I'll go through some data and trials that we've done, and these are showing the effect of adding those enzymes on decreasing viscosity. So here we've got some IFF enzymes, 3 different IFF enzymes, and we also have a reference that's available in the market. A few trends kind of jump out here, and this was a 95% rye cook at 20 beer gallons. So that's a 3-to-1 water to grist ratio. We see here for all but one at the bottom, when we increase the dose rate of the enzyme, we do see a decrease in viscosity. And so that is what we expect to see. This one up here is the reference is the viscosity reduction is similar as far as increasing the dose, but the viscosity across the board is much higher. So it's not doing as well as the other enzymes in reducing viscosity. And so you're looking here anywhere from at an equal dose rate, 50 to 70% greater viscosity. So that one, that's interesting that it's so much higher. Down here along the bottom in this black diamond IFF number 3, we actually did not see a decrease in viscosity when we added more enzyme. It remained relatively flat. And so what that says that even a little bit here goes a long way. So a lower dose can help just as well as a higher dose. So here you would want to stick with the low dose and you'll get the same effect. Now, in this different trial, we looked at some of the same enzymes again, so number 1 and number 3, but we changed where or when in the process we're going to add them. And this is a different recipe. I think this is probably a bourbon, and that's what, 23 beer gallons, so 3.3-to-1 water to grist ratio. So number 1, we added at the cook, so that's at the start of mashing. The dose rates here are less than what we saw in the previous slide. So we have at the cook 3 different dose rates, an increasing dose rate. And then we have number 3 is added at the cook as well. This viscosity is measured at the end of the mashing. So basically at fermenter set, we've taken a sample and measured viscosity. We see here actually the best effect, at least in this setup, is when we add number 3 at conversion. So we've mashed in, we've done our cook, we've increased the cook temperature here was 203 degrees Fahrenheit. We've cooled down, and on the conversion, we have added the enzyme. So you have a much lower viscosity here. This one here, the green line, is a split dose. So it's the same amount that's been dosed, but it's split between cook and conversion. And you can see that it's almost, the viscosity is almost as low as when you add everything at conversion. So looking at this, you might say, okay, that means I should really add my enzyme at the conversion. I would have to agree, but you also have to get a better idea of what the process is. When are you putting in your rye? Does it go in at conversion? If so, then yes, you should put it in at conversion. Or are you putting rye in at the beginning of the mash, and do you need help with reducing viscosity? Or do you have very beefy motors on your agitator, and that increased viscosity during the cook won't be a problem? So those are a few more questions you would need to answer before you decide, yes, I'll put everything in at conversion. No, I can put everything up front at the cook, or maybe I should do a split dose. So it depends upon a lot of variables. But again, we see that same trend. The more enzyme we add, the lower the viscosity at the end. And that's a good thing. That's what we want. As we'll see in the next slide or coming up, you're also most likely going to see a higher ethanol yield. So if we look at some other results from the previous slide, depending upon where you add the enzyme, you reduce viscosity, you have a greater viscosity reduction with the more enzyme you add. And now we're looking at another way to verify if we're doing what we're supposed to do. And we're measuring ARABINOXYLANs, and here it's labeled as PENTOSAN. So as I mentioned earlier, if you can chop up those ARABINOXYLANs into smaller and smaller pieces, if you can take those large chains and smash them to bits, you'll have more pieces to count. You can measure the concentration in solution. And so that's what we're doing here. What's the concentration of pentosan? So the more enzyme that we add, the more pentosans we have. So we expected to see a lower dose rate, and we do expect to see more pentosans in solution because we have more and more of those smaller pieces in solution now. And as we make those smaller and smaller, we limit their water binding capacity, and that's how we reduce the viscosity. There's always an outlier here, so somebody would have to go back and investigate, well, there's no increase here on IFF number 1, it's relatively flat. And so when you're doing your application work and you don't know the answer, you always can say that needs further investigation. And that's how I'll leave it here. Finally, I mentioned beta-glucans are another non-starch polysaccharide that are known to cause viscosity. And looking at these two enzymes, again, one of the blends does have a beta-glucanase in it. One of the enzymes has a beta-glucanase component. So we've actually reduced beta-glucanase to 0 here. So there's no more, beta-glucans. No more beta-glucans in solution. For the others here, and that's my screen's covering that up. So that's going to be added at the cook or the split dose. We still have beta-glucan in solution in a fairly stable amount, no matter the dose rate. So again, the viscosity decreased, beta-glucan is the same, and so that again indicates or supports the idea that it's the ARABINOXYLANs that are causing the viscosity. So we've been able to reduce the amount of ARABINOXYLAN, we've reduced the viscosity, and it's really what you need to focus on. It's the ARABINOXYLAN in the rye that's causing the viscosity problem. Finally here, getting to one of the other benefits of breaking down that cell wall material that surrounds the starch, you allow the other enzymes in the mash, the alpha amylase, the glucoamylase, the beta amylase, you allow better access to the starch to liquefy it. So first gelatinization, liquefaction, and then conversion into fermentable sugar. And this is going back to the very first chart that I showed you. Again, with an increasing dose rate, we got, for the most part, an increase in ethanol yield. And that's because we have better access to the starch in there. And so we would, again, have to look a little bit deeper here and figure out why these two, with an increasing dose rate, didn't see an increase in ethanol. But certainly with IFF number 1, we see that increased dose rate results in or leads to increase in ethanol, and then IFF number 3. So in addition to reducing viscosity, we also get more ethanol out of it. Finally, this is just an interesting note at the end. This is a different way to look at the viscosity from the very first slide and the last slide I just showed to you. We always run a control in these trials with no enzyme. We want to make sure that things are working the way they should. And it's an error here because the mash was so thick, we could not get a sample and we could not analyze it for viscosity. That's how thick it was. And so you can think about that on a production scale. If you're not using enzymes, you're really going to have a lot of trouble with viscosity. I'm not showing it here, but we also measure for ethanol. And we always see less ethanol in these control mashes as well. So you have a high viscosity problem and you get lower yields. From rye especially, which is already limited in the amount of ethanol that it can provide. So you can choose not to use enzymes, but if you do, it can be quite costly. And in the end, you're leaving money on the table. You're paying for these grains, you're basically paying for the starch, but you're not utilizing it. You're not fully utilizing it and converting the starch to ethanol, and you're creating a lot of production problems in your distillery. So enzymes can very easily help you overcome these problems. So just to wrap it up here, if you're troubleshooting, make sure you know what's causing the problem there, right? If you have rye, you definitely need to use a xylanase. Otherwise, you'll have high viscosity. Beta-glucan also can cause high viscosity. That needs a beta-glucanase. And starch can cause high viscosity, and that needs an alpha amylase. And sometimes your processing time might not be long enough, or the amount of malt you have in there might not be high enough, or your temperatures could be off. And so it's very easily, especially with alpha amylase, to have problems with gelatinization and liquefaction. So alpha amylase can be quite sensitive there to those process variables, time and temperature. So when it comes to rye, we would recommend our first choice, Laminex C2K. It's proven to be a very good performer with good results. And we at IFF, along with Gusmer Enterprises, are always happy to help you troubleshoot and optimize your process. We do this free of charge, and we're always interested in every time we help customers. It's always been a very good experience, and we meet a lot of really good people out there in the industry looking to do a better job and make a good whiskey. So that's it for now with my presentation. And if we have any questions, I will go ahead and answer them.
We have another question. So as far as the dose rate, it seems that from the charts presented, 0.5 kilograms per ton is the optimal addition. Is that correct?
I think it depends which enzyme you're using and the conditions. You could start at 0.5. I think really to optimize it in your own production facility, you have to do a few different dose rates and find out which one works best. But I mean, that generally speaking, that sounds like it's in the right range, maybe on the low side.
There was another question too about what the best process to cook rye. Is there rest phases like other grains?
Yes, and I think the key there would be gelatinization of the starch. Now, in our lab, we normally recommend 60 minutes at your gelatinization temperature. I don't think anybody would be too happy at 60 minutes for each rest. Can you get away with 30? Most likely. Anything less than that, I think, would be problematic. So 15 minutes might be too little time. It depends upon the thickness. So how many beer gallons? The gelatinization temperature for starch varies, even from the same grain. So the same variety grown in different locations based on weather year. So there are a few variables. And so that's why when you look at gelatinization temperatures, there's always a range. But that's the key. The key is gelatinization. So you have to hit a certain minimum temperature, and you need to hold that temperature for a certain amount of time.
All right, next question. Where would be the best place to purchase your enzymes for us in Canada? Guzmer does sell into Canada, so feel free to reach out. We can put you in contact with someone that can help you. Then I'll go on to the next question. How much different between 95 5 rye malt and 30% corn inclusion? Not quite sure what the question is, how much different between rye malt and 30% corn inclusion? How different the processing may be, or how difficult? You could kind of elaborate on that question. It would help us get you a good answer here. But while we're waiting for that, I'll move on to the next one. What pH were these studies completed at?
Yes, you can see me shuffling through my papers. The slide B, so 23 beer gallons was a pH of 5. And the first one, A, at 20 beer gallons and 95 rye, that was pH of 5.5.
Great, thank you. All right, we did get a response here. How much does the 30% corn inclusion in help with viscosity?
And what was so if you had, and the previous question was what, 95?
So if you're looking at 95, yeah, 95.5 rye malt versus adding a 30% corn inclusion.
Well, you should probably see some changes in viscosity. You're reducing the amount of ARABINOXYLAN, but you still have starch to deal with. So a few different variables. Obviously, there's going to be a change. How much, I think, is probably the bigger question. How much of a change would you see? And are you happy with the results? You probably get a different spirit as well. So a lot of things to think about. So you can give us some more information there. Maybe help answer that question if we haven't already.
Okay, thank you. Yes, and obviously, if you have a question later on, or if something wasn't answered maybe completely, feel free to reach out directly to us. We will definitely try and work with you through some of these questions. We have another question coming in. Will substituting a portion of rye in the mash with malted rye help with viscosity?
Most likely it should. I would say there you're still going to deal with the starch. And so you want to make sure you gelatinize the starch in there. But all things being equal, yes, if you have malted rye, that seed has germinated and it's broken down some of the cell wall material. Now it depends on how intense the malting process was, how long germination was allowed to proceed. And so those are some more things you would have to look at.
Thank you.
So possibly it should help with viscosity.
Okay, we have another question. How would reintroducing spent mash into the ferment affect viscosity?
If you're going to reintroduce it, so like a sour mash, you're diluting it, so you should see some reduction in viscosity. You would have to be careful about pH changes. If you get too far outside of the pH range where these enzymes, so xylanase or your other enzymes, your glucoamylase, your beta amylase, and alpha amylase. So if you're adding a sour mash or spent mash back into the ferment, I would be careful about pH range and any changes in pH. And that would be a good plug for exogenous enzymes. they operate over a much wider or broader pH range than the enzymes that are found in your grains. They do the same thing, but they have a much broader and much broader pH range.
I think that was all the questions that popped up. We do still have some time, so if you've got any other questions or comments, please go ahead and use the question and answer box below and send us. Oh, we did get another one here. For a recipe with similar amounts of corn and rye, when would we switch from wanting to go more heavy with the alpha amylase versus the C2K enzyme? As in, which would be more dominant or beneficial?
Well, the alpha amylase and the xylanase are working on two different substrates. So that's why one of the key aspects of enzymes are very specific to what they do. Your alpha amylase would be helpful to liquefy the starch. So first you'll gelatinize it, you'll break open the starch. That's just a function of water and temperature. So you have to heat it up to that gelatinization temperature. It's going to be much higher. The gelatinization temperature for corn is much higher than rye. But once you burst open the starch, your alpha amylase will help break that down. And that's your first step in converting it to fermentable sugar. So alpha amylase would help for both grains. The xylanase, then the C2K, is going to help you with the viscosity that's coming from ARABINOXYLAN, and that's mostly coming from the rye. If you remember back to the chart, the amount of ARABINOXYLAN in corn is actually fairly low. So I think they would both be helpful. But if viscosity and plugged heat exchangers and overflowing fermenters and stuck mashes is a problem, and you have rye in there, then I would look first at the Laminex C2K.
Thank you, Andrew. We have another question. Oh, actually, another comment. Thank you for answering that. Okay. Any other questions or comments? Oh, there's another one. Currently using alpha amylase, beta glucanase, and glucoamylase in our mash, would you recommend substituting one of these with xylanase or to use in addition to these?
You can probably substitute the beta glucanase. So your alpha amylase and glucoamylase are turning your starch into fermentable sugar. So I would leave those two as is. Those are very important. They work together for primarily viscosity, but again, also for boosting your yields. And if you have rye, xylanase would be helpful, but it depends upon what your grain bill is as well. So again, beta glucanase works on beta glucans. That's a non-starch polysaccharide. Xylanase works on ARABINOXYLAN, and that's also a non-starch polysaccharide, but they're two different types of non-starch polysaccharide. So you'd have to find out, based on your grain bill, most likely which one is causing the problem, and I would attack that first.
One other one. Would you recommend dosing higher with sweet mashes, pHs greater than 6.3, than sour mashes, which are less than 5.8?
I would have to go back and look at the pH curve. I don't think you'd have to. I don't think you'd have to dose higher. The activity range for something like Laminex C2K, I believe, would fall within that range. Certainly less than 5.8. That's not a problem. But I think 6.3 or greater is still within range where you'll get very good activity. So just guessing here, but 80% activity or higher, I think you'll still have that and you should have no problem. But if there's any specific questions, we can certainly dig into that and look at the details later on if you're willing to contact Gus or us or Gusmer, and we can spend some more time on that.
Okay, thank you, Andrew. We have another question. Will a higher viscosity help with any foaming issues during a stripping run?
Normally, viscosity leads to increased foam. So higher viscosity is leading to more foam or longer lasting foam. So as bubbles form and coalesce, the liquid is really on the surface of those bubbles. And the faster that liquid drains due to gravity, the faster the collapse of the bubble. So if you're slowing down the drainage of the liquid through viscosity, that foam is going to last longer. So you want to reduce viscosity.
Okay. Well, as Andrew mentioned before, if there are any other specific questions or issues that you would like to comment on, feel free to reach out to either GUSMR or IFF, and we'll definitely try and work with you through those questions. Once again, a copy of this presentation will be emailed to everybody in this group later on. If there are no other questions, I'd like to thank Andrew for his time and for giving a great presentation. I thought a lot of the points that you made could be very helpful with processors that are using rye. So thank you, Andrew.
Great, thank you. Thank you for having me. And again, thank you to everybody for joining.